anyone. You can check your exam schedule on your personal schedule, or you can look up the Western University exam schedule to find your location. You need to make sure that you go to your location so that you have an exam ready to go for you. The resource room is open this week, so if you have any questions on how to solve any particular problems, this is the week to do it. Solving these practice problems from the workbook is the #1 best way to study for this type of exam. Do you remember bubble soccer from last class? For a reaction to occur between two species, they need to collide. And they need to collide with sufficient energy to overcome that activation energy barrier. They have to smash into one another in the correct orientation as well. We introduced the idea of these reaction coordinate diagrams, and we need to know how to interpret these reaction coordinate diagrams, where a reaction could be thermodynamically favorable. It could be exothermic, where the products have a lower energy than the reactants. But in order for the reactants to get to the products, they have to overcome this activation energy barrier. And this could be really big, it could be really small. It doesn't really have much to do with the delta G or the delta H between the reactants and the products. But the height of that activation energy, how steep it is, how hard it is to get over that barrier, determines the rate of the reaction. So how do we go ahead and actually measure the activation energy for a particular reaction? Well, we can do some experiments. Just like rates need to be determined experimentally, the order of the reaction needs to be determined experimentally, so the activation energy also needs to be determined experimentally. Okay, I'm still hearing a lot of side conversations, so I'm just going to ask you to wrap it up so that everyone around you can hear. We've seen the rate law before, where the rate of a reaction is equal to the specific rate constant K, and then the concentrations of the reactants or products to some coefficient power. We can determine that experimentally by doing multiple experiments and changing the initial concentrations and seeing how the rate changes. But how do we figure out other aspects of the rate law, such as the activation energy? Well, the specific rate constant K has a whole bunch of information wrapped up in it. It's like a little gift-wrapped package that includes A, this probability factor of the reaction going forward. It includes the activation energy. It includes considering the temperature. And it helps to determine how fast or slow that reaction will be. Well, if we want to figure out what that activation energy is, especially if we don't know what this probability factor A is, we can do 2 experiments and compare their rate. But this time, rather than changing the concentration, like we did when we wanted to figure out the order of the reaction, we keep the concentrations the same. We keep the reactants the same, the products the same, everything the same, except for changing the temperature. If we start the reaction exactly the same, just with the temperature, well, the concentration of A and the concentration of reactant B will factor out. Any change in rate isn't due to that initial starting concentration because it was the same. That allows us to compare experiment number 2 to experiment number 1 and compare their specific rate constant Ks. Well, based on the Arrhenius equation, we know what K is equal to, and you can see it written up there on the screen. This probability factor A isn't going to change by changing the temperature of the reaction. So if we're comparing these 2 experiments, we can factor the comparison of these out as well, because it's the same value. That leaves us with the ratio of these 2 exponents. Well, I want to be able to isolate what this activation energy is. So I can take the ln of both sides of my equation. So I'm going to take the ln of the ratios of the rates and the ln of the ratios of the specific rate constants. Now, if I have ln of a fraction, another way that I can write that out is the numerator minus the denominator. So I can rewrite this equation following mathematical rules, where it's the numerator minus the denominator. And you probably remember that if we have the ln of an e, that allows us to bring the exponent down. And the first exponent is negative EA over RT2. And then we have the minus negative EA over RT1. A minus and a minus gives us a plus. It's just easier to start an equation with a plus factor. So we're going to start with 1 over T1. Both of these components have EA over R. So I can pull out this EA over R factor and then multiply it by 1 over T1 minus 1 over T2. And then I say, well, what was this equal to? This was equal to the ln of the ratio of the rates. Now, if I can do 2 experiments and determine what their rates are and take note of the temperatures that I'm doing these experiments at, I can solve for EA. R here is just the gas constant, 8.314, but now we're going to measure it in joules per mole Kelvin rather than liter kilopascals or other units. So we have this really handy formula to solve something by comparing 2 pieces of experimental data. Or, if we know the activation energy, we can predict forward to another temperature where we may not have done an experiment yet. So let's see how we can apply this. When the reaction temperature was increased from 20 degrees Celsius to 30 degrees Celsius, the rate of the reaction increased according to these values as well. Part A asks us to determine, well, what is the activation energy for this reaction? And we'll leave part B for the next slide. Well, if I see 2 different temperatures, 2 different rates, and otherwise everything is the same, I can pull out this really handy rate comparison law. I want to solve for the activation energy, and now I just need to identify what's my rate 1, what's my rate 2, what's my T1, and what's my T2. As long as you consistently match the temperature with the rate, it doesn't really matter which one you specify as 1 or 2. I'm going to make my bigger numbers into option 2. So that means 20 is going to be my T1, and 30 degrees Celsius is going to be my T2. The first rate is my rate 1. That corresponds to 20 degrees Celsius. The second rate value will be the rate for the second experiment done at 30 degrees Celsius. Well, if I'm comparing these temperature values, I need to make sure I'm using absolute temperature scale. I can either remember that I always need to do that, unless I'm using delta T and just taking the difference between the 2 temperature values. Then delta T is the same in Kelvin and degrees Celsius. 5 integer difference, 5 integer difference, it's the same. Another way to remember is that the gas constant is in units per Kelvin. And that's another great way to remember that we need to convert these temperatures to Kelvin. So I'm going to write down, instead of 20 degrees Celsius, 293 Kelvin, and temperature 2, 303 Kelvin. I now have my rates, my temperatures. I've written down my variables so I can keep them straight. We can now plug in the values and solve for EA. So therefore, by carefully identifying my variables, knowing which is associated with experiment 1, which is associated with experiment 2, I can solve for the activation energy and see that it's 3.47 times 10 to the power 4 joules per mole. And that's the height of that hill that I have to overcome to get this reaction going. Well, I have 2 data points now. I know the temperature and the rate. Now that I have 2 points, I can extrapolate in either direction. We've done this experiment at 20 and 30 degrees Celsius. What if we extended this one way and predicted what the rate would be at 100 degrees Celsius? We can do that. We now know what the activation energy is. We could compare 2 new temperature values and use one of these rate values to predict the other rate value. So for part B, we're going to extrapolate and extend this and predict what the rate will be if we cranked this reaction up to 100 degrees Celsius. Now, my formula still says rate 2 compared to rate 1. We need to turn one of these into experiment number 3, whichever. We could compare experiment 1 or 2 to 3. For simplicity, I'm just going to choose experiment number 1. Just make sure you select consistent data. I want to solve for the rate at this new temperature. I know what the temperature is, 100 degrees Celsius, but in Kelvin, that will be 373 Kelvin. We now know what the activation energy is because we solved that in the previous problem. We know what R is all the time. We know what the rate 1 is at 20 degrees Celsius. The only thing we don't know is the new rate at 100 degrees Celsius. We've identified our data, we've selected an appropriate equation, and we can solve for rate 3. Doing some math, I can isolate this to the ln of rate 3 equals 3.46. I'm going to take the e of both sides to be able to isolate the rate 3. So we can now take a look at this and say, well, does this number make sense? When we started at 20 degrees Celsius, the rate was 1.5 moles per liter per second. When we increased the temperature by 10 degrees Celsius, the rate increased to 2.4. If we jump this from 20 all the way up to 100, we would expect the rate to be even faster. And indeed, this rate is faster, almost 32 moles per liter per second. That's pretty fast. So we can do this with specific data. Or we could say, you know what, I don't have the specific data, but I still want to know how many times faster it could be if I cranked this temperature. Hypothetically, I could pay an employee to monitor this reaction for 10 hours, or I could pay this employee to monitor this reaction for 1 hour. How fast do I want to make my product? Well, there are a lot of factors to consider, but if simply increasing the temperature can increase the rate of the reaction safely, and you're not paying too much extra electricity for that extra heat, maybe that's what you want to do. Okay, so let's look at one more problem with this activation energy. This time, we're told what the activation energy is at a particular temperature. I want to predict what temperature I need to use to get this reaction to be 30 times faster. Based on the bottom line, this is how fast this reaction needs to be for us to be able to make a profit, or our desired profit. Well, what does that mean? It means the ratio of the faster rate compared to the slower rate is 30. I need the ratio of rate 2 to rate 1 to be 30. I don't know what either of those values are, but the ratio is going to be 30. Doesn't matter what the specific rate constants are at this point, because I'm told the activation energy. I always know what the gas constant is. I know for experiment 1, my temperature is 298 Kelvin, and I want to predict what temperature I need to use to get this reaction even faster. The activation energy here is given in kilojoules. My gas constant is in joules, so I need to change one of them to make sure that my units are consistent. So let's go ahead and do that. I'm going to change my activation energy into joules per mole to be able to factor out nicely with my gas constant. So for the principle of this problem, we need to know which formula applies, which data to use, what our end goal is, watch our units, and then we also need to be able to do some math. So if isolating for a particular variable is sometimes challenging, or you can't always get to your correct desired answer, chat with one of your classmates or drop by the resource room to figure out how to be able to calculate the correct answer with your Sharp EL510 series calculator. Or if you're amazing, do it in your head. Okay, so on the previous problem, I'm going to grab your attention again. On the previous problem, we had 2 experiments that we started with. And then we extrapolated to a new temperature. This may be reminiscent of interpreting a line. And I hope you're not really sick of looking at lines. I'm getting a little bit sick of it myself, but we can actually graphically interpret reaction rates. And we can get the equation of a straight line, where we can do 2 experiments and then extrapolate one direction or the other to be able to predict a new temperature, or to predict a rate at a specific temperature. Here we have the Arrhenius equation that we started with previously. We can take the ln of both sides. So that gives us the ln of the specific rate constant, and then the ln of the A multiplied by E. Mathematically, we can take the ln of the first component and add the ln of the second component. Well, the ln of the second component is an E, so we can bring that exponent down. It has a negative sign. So we end up with this handy equation that you see on the second line. Well, I can take the ln A, add it to the other side, and then I have this formula here that again reminds me of the equation of a straight line. This just gives us a richer way to be able to interpret our data and to be able to predict either way what the temperature or rate may be. Based on this formula here, we can see that ln K is the y-axis. So we can plot the ln of the specific rate constant along the y-axis and the ln of 1 over t as our x-axis. Based on this, I would like you to finish interpreting this graph. Chat with the person beside you. Based on what we've assigned so far, what is the activation energy, and what is A for this reaction? try logging out and logging in again. Okay, and 10 more seconds. And 3, 2, and 1. Okay, well done. 3/4 got to C as the correct answer. No votes for E, that's good. Okay, so simply by looking at this graph, no memorization required, you simply interpret the equation of a straight line and see how the different components line up. If negative EA over R is the slope of the line, and calculating the slope of a line is a relatively easy task in the scientific community. We can do that. If we want to solve for EA based on this formula, we simply multiply both sides by R, divide by -1, and we end up with negative MR. You read the graph, and now you know the activation energy of your experiment. So you could compare the 2 data points if you only have 2 data points, but if you're given a graph or something to be able to make a graph, again, we can solve for that activation energy. And then we know that once we have that activation energy, we can extrapolate and predict what may happen. Here we have our y-intercept. It's equal to ln A. So if we simply want to isolate A, you can see we simply take e to the power of that y-intercept. Well done. Well, we know how to solve for the activation energy now. And we know that if we increase the temperature, we can increase the rate of a reaction. Oftentimes, we do want faster reactions. Sometimes we want slower reactions. In a fridge, we want slower reactions. That's why we put our food in the fridge, to slow down those decomposition reactions. So our food lasts longer. That's why we change the temperature. And if we want it to go faster, we've seen this slide before, this is old news. We can increase the temperature. That broadens the distribution of the kinetic energy of those reactants and allows some to be able to meet that activation energy requirement and overcome that barrier. But what if increasing the temperature isn't an option? Let's think about our bodies. If we need a reaction to go faster, we can't just say, oh, well, we'll just put you in an oven and crank you up to 100 degrees Celsius. It makes your reactions go faster. That's not going to work so well. After just a couple degrees, your proteins are going to start to unfold and your body will fall apart. Not a good idea. So we need another way to increase the rate of a reaction. What if we could simply lower the activation energy without messing with the temperature? And as you can predict, that's where catalysts come in. Catalysts lower the activation energy for a reaction. Here we have this reaction coordinate diagram. It's hard to get up in the morning. You need a big kick in the butt to get up, and then you get to have your wonderful day, right? It's hard getting out of the covers and waking up, and it's cold and it's loud. But if someone comes and brings you a house coat and brings you a cup of coffee, it just lowers that activation energy. It's still a little painful to get up, but it makes it easier. This is what catalysts do. Catalysts could be proteins, and the enzymes in your body, a lot of them are proteins, where they have a specific shape, and they can say, hello, reactant, I have a nice little spot for you here. Hello, other reactant, I have a nice spot for you here. I'm just going to bring you together at just the right orientation. I'm going to stabilize this transition state, make it easier for you to react, and then I will let you go, and you can go on and have a happy reaction life. Kind of like a dating website, perhaps. It says, hello, person. Hello, person. You could randomly wander around Western University campus over the next 4 years, and maybe you'll bump into one another with the right energy, with the correct orientation. Maybe that will happen. But if we say, hello, person, I'm going to smash you together right now, pair you up, maybe something will happen. Or if there's just one reactant, an enzyme can take that reactant and say, okay, I have a special little spot. All your extra electron density can fit with this extra positive area. And where you're electron deprived, we have some extra electron density over here. We can stabilize your transition state to help you go through this reaction. Catalysts lower the activation energy. We have biological catalysts like enzymes. We can also have metals. Certain metals can act as catalysts for certain types of reactions. So they lower the energy by providing another way for that reaction to happen. This is just easier. That stabilizes the high energy transition state. If we lower that activation energy, then we can increase the rate of the reaction. And this catalyst can be used over and over again. It says, okay, here you go, smash you together, away you go. Next one, here, smash you together, and off you go. A catalyst can be reused, it's not consumed. Here's an example. Glucose turning into pyruvate. What is the name of that process? Go ahead, shout it out. Glycolysis, that's right. Now, from Hess's law, you do not need to memorize this, okay? You don't need to memorize this part. Hess's law says that the delta H for the overall reaction is the same as the sum of its parts. You could have some glucose in the morning, some extra sugar with, well, that's sucrose, but approximate, a type of sugar, and you could light it on fire, combust it, and it's going to give off some energy. We don't want that happening after you eat your Fruit Loops in the morning. We don't want these internal combustion reactions happening and exploding your digestive system. So that's not how our body processes the glucose. Instead of one big boom reaction, like happens in your barbecue, every tiny little step is controlled. Every tiny little step has an activation energy and reactants and products and a specific rate constant. Tiny little steps that give off tiny little bits of energy that your body can use and do something with. Through this reaction, you can see a whole bunch of words in blue letters, and they end in A's, hexokinase, isomerase, kinase, idylase, all these different A's, and those tell you that they're enzymes. These are biological catalysts that are just the right shape to act as a catalyst for that specific step of the reaction. We want to look at one particular step in this process. Step 4 to step 5 actually produces two products. One is a ketose, so it has that ketone part of the sugar, and the one is the aldose. It has the aldehyde and an alcohol. Well, we need both products to be the glyceraldehyde 3-phosphate to continue on with this process. So our bodies use this triose phosphate isomerase. See how it ends in A's? It's an enzyme. It catalyzes the reaction. This TPI enzyme catalyzes the reaction of the ketose back to the aldose so that it can continue on to make your pyruvate and produce energy for your body. Well, if someone has a DNA mutation for the production of this particular enzyme, this can result in triose phosphate isomerase deficiency. It's a rare disease where your body doesn't quite make the right TPI protein enzyme. This often leads to early death. It can lead to neurological issues, muscle issues. You can imagine that every living thing needs to be able to, well, not everything. A lot of things need to process sugar, right? Every animal at least. And if you can't, or if you can't do it really fast, that can lead to serious biological issues. From a chemistry perspective, we can analyze this particular enzyme with what we know about rate laws and take it a step further. The specific rate constant for this catalyzed reaction is 4 × 10⁻³ . To help visualize this number, I'm going to write it out. That's the specific rate constant when this reaction is catalyzed. If it's uncatalyzed, if we don't have this TPI enzyme, the specific rate constant is 1, 2, 3, 4, 5, 4, 3 per second. Well, what's the difference between these two specific rate constants? We can calculate the rate enhancement factor. How many times faster is the reaction because of the presence of this catalyst? So we can take the 4,400 and divide it by the little number, and we get a really big number. We get 1 billion. The catalyzed reaction is 1 billion times faster than the uncatalyzed reaction. To help us grasp how big that number is, if the catalyzed reaction took 1 second to happen, ketose into aldose, and then you can continue with your glycolysis. Catalyzed took 1 second. That means the uncatalyzed would take 32 years. We don't have 32 years to wait for our glucose to be metabolized. This enzyme is it's called catalytically perfect. It works as fast as it possibly could. It's simply limited by how fast the reactant can get to that enzyme and get kicked out. It's just so fast, and this enzyme can be reused 1 billion times faster. Well, how can we calculate the difference in activation energy due to the presence of a catalyst? What is this decrease in activation energy that happens because of the presence of a catalyst? Well, as you can probably predict, we're going to need to do some experiments. If we do everything the same temperature, same concentrations, but we only change whether or not a catalyst is present, we can measure that difference in the activation energy. So we can compare the rate of the catalyzed reaction to the uncatalyzed reaction. We keep the reactant concentrations the same to keep our lives easier. That allows us to isolate for the specific rate constants. When we write out the specific rate constants according to the Arrhenius equation, we can see that the A probability factor factors out. Same that we did before, we can take the ln of the ratio to bring these exponents down. Both of these exponents have RT in the denominator. We did these experiments at the same temperature. It's really helpful if you only change one thing at a time. So same temperature, we really are only measuring the difference in the activation energy. How do we remember for delta EA which one to subtract from which? Well, we want to take the big number and subtract the smaller number so that we have a positive number left over. So we now have a handy formula. The change in activation energy is equal to the ln of the ratios of the rates. So let's go back to our TPI enzyme example, our triose phosphate isomerase. We know that with the catalyst, it's 1 billion times faster. That's amazing. By how much does this enzyme reduce the activation energy? Well, we were told the specific rate constant values already. So we know what these two values are. We're told that both experiments take place at 298 Kelvin. We always know what our R constant is, which allows us to solve for the delta EA. So now it's simply placing the numbers in this relevant formula and solving for EA. Therefore, the activation energy decreased by about 5,000 joules. 50,000 joules. 50? 5 times 10 to the power 4. Big, big decrease because of the presence of this catalyst. Okay, so you can see that we're accumulating more formulas that allow us to compare the rate of a reaction, looking at activation energy, or temperature, or the presence of a catalyst. We need to know what our tools are so that we can grab the right tool to solve the appropriate problem. Let's do one more. Here we have a catalyst, and it lowers the activation energy, as we know it already does, down to 70 kilojoules per mole from 100 at a particular temperature. By what factor does the rate of the catalyzed reaction increase? We have another one of those ratio problems. We don't know what one of the rates, or even both of the rates are, but we simply want to know the comparison. How many times faster will it be? So it's this ratio that we want to solve for. Now again, we have a couple different rate comparison formulas on our formula sheet now. We have to choose the one that's relevant to this problem. Here we're given 2 activation energies. Odds are we need to be able to compare them, which is indeed what this formula helps us to do. We can use these 2 values to calculate the change in activation energy. We're going to pay attention to the units here and solve for the ratio of these rates. So the change in the activation energies, I'm going to move everything to joules to match the units of the gas constant. So 100 kilojoules turns into 100,000. So here we can see that by using this catalyst, we can increase the rate of the reaction 1.67 times 10 to the power 5. If the catalyzed reaction was 1 second, for example, the uncatalyzed reaction would take 46 hours, 2 days. Our biological reactions happening in our body, we don't have time to wait 2 days for one specific step to happen. This is why our body has so many unique catalysts, and why a lot of companies in industry use catalysts as well. So we've learned how to solve for the rate of a reaction, figure out what those exponents are, what the order of the reaction is. That helps us figure out what integrated rate laws to use. And then we can also compare reaction rates in different reactions by exploring temperature changes or adding a catalyst. The final piece of the puzzle in this course is applying this to reaction mechanisms. And this is a lot of fun. It's kind of interesting to see how we can take rate laws and now do something pretty cool with it. Scientists can compare rate laws, measure rate laws under different conditions, not only figure out ratios of rates and temperature and catalysts, but they can also use clues from how fast or slow a reaction goes to predict what's actually happening at the atomic level. what is smashing into what, and then what happens next. And we're going to learn some terms and how to interpret and predict reaction mechanisms. For example, how does this particular reaction occur? Here it looks like we have two molecules of NO, nitric oxide, smashing into chlorine gas to produce nitrosyl chloride, or NOCl, two molecules of it. That's cool, but is that what actually happens at the atomic level? Do we need two NOs and one Cl2, three different molecules, to simultaneously smash into one another with the correct energy at the correct moment, in the correct orientation to make that reaction happen? Well, no. It would be statistically very, very, very low to get three molecules to collide at exactly the same moment in just the right orientation for any meaningful reaction to happen. What actually happens is that the reaction occurs in two elementary steps. So this is the first term that we need to know and understand and to be able to apply. An elementary step is an event. It's one action, one tiny step in the process. What actually happens is that chlorine smashes into the first nitric oxide to produce NOCl2. Now go back up to that overall balanced equation. You don't see NOCl2 in this overall reaction. It's produced, but it doesn't end up in the overall reaction. NOCl2 is classified as an intermediate. It's formed in step 1, but then it's used up in step 2. This is the definition of an intermediate. If we froze this reaction part way through, we could probably collect some of that intermediate and detect that it actually existed. This intermediate then collides with the second molecule of nitric oxide to make our two desired products. Now, each of these steps is a one event thing. It's a one action. It's an elementary step. Each of these steps has its own activation energy and specific rate constant. But then what is the overall reaction? Is it one of these? Is it both of these? How do we know which rate law applies to the overall one? Well, what we don't do is add these up. If you've ever tried to get out of the house with a really slow roommate, maybe your roommate takes a really long time to get ready. Maybe it was like me trying to get out of the house when my kids were toddlers. It's the slowest step of the reaction mechanism that holds back everything. You could get really ready really fast for an upcoming party, but if your roommate is really slow in getting ready, you're not getting out the door until the slowest person is ready. And this explains the rate determining step. So we need to identify what that rate determining step is, and then this gives us insight into that reaction mechanism. Two more terms before we can actually go ahead and look at some reaction mechanisms. One term that we need is unimolecular. A unicycle has one wheel. A unimolecular elementary step has only one reactant. If we have an elementary step, and if we're analyzing an elementary step, that means only one action is happening. If the elementary step only has one reactant, we can automatically deduce that it is first order. There's only one reactant, therefore it's first order. I told you at the beginning of this unit that we couldn't derive those little exponents, the order of the reaction, based on the reaction. And that was true. We can't derive the order of the exponent based on the overall reaction. But if we're looking at an elementary step where only one thing happens, we are allowed, under this special circumstance, to correctly identify the order of the reaction based on the number of reactants. So if it only has one reactant, immediately and confidently we can say that this one elementary step occurs according to first order kinetics. So bimolecular, just like a bicycle has two wheels, a bimolecular reaction has two species. It could be two of the same species, like two A's, or it could be A and B. Simply by having a bimolecular reaction, we can determine that the reaction is second order, only because it's an elementary step. So if we have two A's smashing into each other, that elementary step occurs according to second order kinetics. If we have two different reactants, well, 1 plus 1 equals 2. The overall reaction order is 2. When we come back next class, we're going to apply this to a cool reaction mechanism. Have a great day.